Hi everyone, I'm Pimpanuwat from the Georgia Bank Center for Astrophysics. I'm going to be presenting ALMA observations and 3D modeling of high-J SIO mesas. So, as you may know, SIO mesas are found in the innermost regions close to the stellar surface and are key to studies of the inner wind morphology, as well as the process of dust formation. Here we focus on high rotational state transitions observable with ALMA band 6, which provides different information compared to the typical SIO 43 and 86 GHz lines. Now this work forms part of the Atomium Large program, where we observe 17 AGB stars with a wide range of mass loss rates and various stages of evolution. And that obviously allows us to determine any systematic morphological change both during and after the AGB phase. Now in this talk, we will have time to focus on two targets, Pimpanuwat and R Hydrae. So if you're interested in other sources and future publications, you can check out our website and the science paper by Destiny et al. Okay, so starting with Pimpanuwat, what we have here is the fitted mesa component map from the ALMA extended configuration dataset. There's an interesting region towards the south of the source where there's a curved trail of entirely blue shifted components. Now, together with the vibrational ground state transitions as shown in the top panel, we can infer the existence of a spiral, and there is also a flow of material between the primary source and the companion. So essentially, there is a binary interaction there. Now, most of the mesas are also seen in a ring. This is evidence of an accelerating outflow caused by stellar pulsations in favor of tangential mesa beaming, as you can see here. Now, what about R Hydrae? Well, here we have a similar analysis with Pimpanuwat previously. So here you can see that most extreme projected velocities align along the northeast and southwest axis with the position angle roughly 70 degrees. This result is consistent with the projected semi-major axis of the equatorial density enhancement deduced from CO observations. So that suggests a possible presence of a compact differentially rotating disk in the inner circumstellar envelope of this source. Now let's move on to models. Obviously, we want detailed models to relate observable with the underlying dynamics and physical conditions that cause, mesas. So we are developing a 3D code based on the works by Gray et al. Here we present a 3D model of mesas in a shell-like computational domain, simulating the mesa clouds in the inner circumstellar envelope on the top right, as you can see here. So we have a simulated VRBI image based on the computational domain as mentioned. And from this picture, we can see the effects of cloud overlaps, density and velocity gradients, and saturation of population inversion on the brightness of mesas. And recently, we have added a new capability to the code where we can put a star in the middle of the mesa cloud distribution so that we have a source of pumping radiation closer to the reality that we have with AGB stars. So the bottom panel shows that when the star is present, the level of population inversion drops radially as you go further from the star, as you can see from the right, compared to the left where there's only just background radiation. Now that suggests that we should see a bright mesa spot in the area closer to the star for a given mesa cloud. For project in progress and future work, currently we are analyzing the fitted mesa component maps for other sources in the atomium sample. And we're also trying to find a relationship between the flux weighted projected distances and the mass loss rate. Now, the new model that I just mentioned also needs verification, so that is ongoing at the moment. Soon, we hope that we can make detailed comparisons between the observations and the models, where most of the relevant parameters and realistic distribution of Mesa clouds are included. So yes, that's the end of my talk. Thank you very much for your time and for listening. And I will be very happy to take any questions you may have. Thank you.